Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. To this session, we would like to continue regarding Coulomb's law, but we're going to focus on the third type of source, which is known as surface charge. With that, we like to do problems from handout number 4. I would like to focus on two questions for this particular session, which are question number 1 and question number 2. Okay, from here I would like you all to do yourself other questions in order to make yourself familiarized with the method of Coulomb's law. Okay, so let's do that now. So we're going to do problem number 1 under the category of electric field intensity of a surface of charge. So this is taken from handout number 4. Okay, let's read the question together. Okay, a charge density rho s coulomb per meter squared is uniformly spread over the area of a disk of radius A. So I'm going to draw it. So what we have here, just a disk with radius A, and on top of that disk, there's a surface charge with density rho s coulomb per meter squared. But the question is a bit slightly different compared to before, because the question does not ask us to find the electric field, but what the question asks us to do here, to determine the force on a charge Q that is placed a distance from the center of the disk and on a line that is perpendicular to the disk. Okay, let's draw this problem together. Okay, so we have a disk now. Question number 1. Okay, so I have a disk. So the disk as shown, and then the density of the disk is given as rho s. So with that, it informs us that we are dealing with surface charge. And the second thing that mentioned here is that the radius of the disk is A. Then, perpendicular to the disk, so meaning that, let's say at the center of the disk perpendicular to it, so there is a point charge Q. So we want to determine the force. So the question asks us to do what here? Find the force on Q. Okay, so that should be the objective of the questions. Is there a force? Yes, there's going to be a force, because to have a force, at least we need to have two charges close to each other. So we have first a point charge, second a surface charge. So that combination will create a force. So therefore we need to find the force here. And how do you find the force? From the definition of electric field before, okay, so the force we can determine, in this case the force F can be determined by this equation. So first we want to know the force here. We see there's a charge there, Q, and then we can see that the source of the surface charge going to emit electric field. So therefore, by having a charge an electric field that will produce a force. So therefore, in order for us to find the force, we need to find the E. So therefore, what we need to do now, we need to know E due to what? Due to the surface charge. So therefore, we can see that should be our logical plan in order to solve this problem. Again, I would like to repeat it again what we intended to do. We need to find the force on the point charge. To have a force, we need to have at least two sources close to each other, and from this simple diagram, we can see that is happening. One is point charge, another is surface charge. So now, how to find the force here? We know from the previous equation when we define the electric field intensity, we know the force is equal to the charge multiplied with the E. So we need to find the E first, and then by multiplying with the Q, then we'll be able to determine the force. So how we find the E? The only method that we know at the moment is by using Coulomb's law. So what should be the first step when we want to use Coulomb's law? Should we decide which coordinate system is suitable? And from our experience solving problem before regards of line charge, we can conclude the best suitable coordinate system here should be cylindrical. Then second step, how to make it simple. So make it simple by reducing the number of variables. And also from our experience, by allowing the center or the axis of the disk to be aligned to the z-axis, we can reduce the number of variables. So therefore, we're going to do that. So what I'm going to do now, I'm going to allow the axis of my disk now to coincide with the z-axis. And to make the calculation simple, I'm going to assume that the disk is actually located where? On the xy plane. So therefore, it's going to be quite straightforward now. Yeah, xy plane. Does it mention the actual height of the Q from the disk? Let's check again. Okay, a distance from the disk. So it does not mention. So let's say we're going to define that to be h. Yeah, the height to be h, just to make it simple. Yeah, h. Or you can use z if you want to. Doesn't matter. Okay, so let's do it now. So I want to solve for the force. So how we do it? So again, we're going to take sample. I'm going to take sample. So now the sample must be on our source. So therefore, I have to take the sample to appear on the surface of the disk. So I'm going to choose it to be, let's say I'm going to choose it to be here. Okay, so that should be our sample. So the sample now I'm going to denote as dq. So I know that the radius here is going to be r, okay, and then the height here is going to be h. So that should be my sample location. Okay, and then from our expand the sample based on surface charge, it's going to be denoted as rho s ds. So I'm going to recall that point later on. So let's do that. So first, I have to know the location of my E here. Then I'm going to take the sample here. Then the third step I'm going to do, I'm going to join those 2 points together. So I'm going to join the sample to my E location. So I'm going to define that to be my DE. So I change slightly before I use it to be R, but I know that the direction of R and DE actually the same. So therefore I'm going to define that to be my DE. I'm going to give this arrow, this line as well as my vector R. They are actually the same directions. Okay, so let's define that in terms of equation now. So I'm going to say, based on Coulomb's law, the DE here should be equal to dq divided with 4 pi epsilon naught r square AR. okay, so we know the E location is here. So now I'm going to define my sample dq is what? My dq now should be equal to rho s ds. And based on our cylindrical handout handout 2 table, we can substitute ds now with what now? So rho s remain the same. So ds here, as you can see, is depending on the r as well as the phi. So it should be r dr d phi. And my vector r from the diagram should be equal to what? Should be equal to going into negative rr, moving up h z direction. So it should be my vector r. Okay. So vector r from sample to E location, I'm following this trace. So to create this equation, I'm going to assume to be this component, the horizontal component having magnitude r, but since going into the z-axis, therefore negative r direction, then it's moving upward, the magnitude is h, and the direction is positive z. So finally, what we're going to see now, so our equation now, the dE now, should be equal to, so I'm going to substitute now. So dq should be rho s r dr d phi. Okay, that should be our dq. Then I'm going to choose direction now, negative r plus h z. Okay, I'm going to divide everything with 4 pi epsilon naught because we are assuming the medium is free space. Then should be here r square plus h square 3 over 2. And what I can see here, I can see actually my dE consists of 2 components. Okay, what I'm going to say now actually is consists of dE of the r component vector, because I can see r there, plus dE of which component? Z component. So that should be my respect to which coordinate system? Cylindrical. So what I'm going to say now, actually my dE can be redrawn now. If you look carefully, the dE actually consists of 2 components. One component will be horizontal, which is our DER component vector, which is agree with our equations. Okay, another one should be Z component, so therefore this component. So this should be our DE Z component. So what we can see now from the diagram, our dE vector actually consists of 2 components, the R component as well as the Z component. Why I'm doing this? Because we need to integrate, and when we integrate, mathematics-wise is going to be quite challenging. So we can eliminate or reduce the complexity by using graphical approach, whereby because the charge distribution here is symmetrical, whatever appear on the right, you can also take sample on the left. Okay, and then provided that the distance the same, let's say we take distance to be r, and this should be represent our second sample. And we know that this sample also going to produce its own electric field. Okay, so this should be the electric field due to the second sample. And from the mathematics that we have proven before, this second sample also consists of 2 components. One is the horizontal component, another one is the vertical component. So what we need to do next in terms of mathematics, we have to sum. We have to sum all the electric field produced by all the sample on our source. So what we need to do then, we need to sum all the electric field by using the term of integrations. Okay, so when we sum from this simple analogy, what we can see here, when I sum the blue field due to the blue sample with the black field due to the black sample, I can see from this simple graphical representation that the R component will cancel out. And we're only going to deal with which component at the end of the integration? Yes, the Z component. So therefore, I'm going to assume now I can eliminate or ignore the R component due to this argument. When I sum the field, I can see from the graphical representation, all the horizontal component will cancel out. And we're going to end only with the Z component. So therefore, I'm going to choose that particular component in my final integration, which are the Z directions. And then I'm going to choose rho S. And then I can see there's H there. Okay, and then I'm going to divide everything with 4 pi epsilon naught. Okay, and then I can say to myself, oh, that should be first the R. Okay, there's R dr over R square plus H square, power of 3 over 2. And then I'm going to have the second component should be d phi. So therefore, how many integration that we need to have? 2 integration. Okay, one with respect to R. So R from where to where? From 0 to A. That should be the radius of our surface disk. Then the phi from 0 to 2 pi. Okay, so and then we have done this integration before using table. So by using the same table, I'm going to find the solution. So I'm going to end this integration with simple solution as such like this. The Z direction, rho S, H over 4 pi. Okay, then epsilon naught. So I'm going to end with, for this integral is going to be -1 over square root of R square plus H square. So the limit is what we have seen before, from 0 to A. And then the second integration should be just simply phi, the limit from 0 to 2 pi. Okay, so what should be our final solution here? So therefore, our final solutions our final solution going to be E, equal to Z directions. So I'm going to cancel 2 now. Okay, so first I'm going to substitute with the A, so negative, then should be negative. Okay, so I'm going to have now rho SH over 2 epsilon naught. Then I'm going to have now should be 1 over H minus 1 over square root of A squared plus H squared. Okay, that should be our solution for the E. But yet we have not answered the question of number 1, because our question number 1 insists that we determine the force. So the force we're going to write here the force on the Q. on Q will equal to F equal to Z, still the directions, should be rho S Q H over 2 epsilon naught 1 over H minus 1 over square root of A squared plus H squared. Okay, that should be our final solution for question number 1 of handout 4 regarding electric field intensity due to surface charge. Okay, so that's quite interesting. So I think you can see the way we solve it together is very systematic, and we still repeat the same method as what we have done for the line charge, but the only difference here, the surface charge is our main concern. Therefore, due to that reasoning, the mathematics become a bit complicated where it need to be solved using double integration. But still, the mathematics is manageable, and then you going to get the solution to the problem. Okay, so let's go further on. So let's say I want to find the field due to infinite surface charge. So we're going to make it slightly specific now. Yeah. So we want to find the electric field due to infinite surface charge. Okay, that should be our concern. So I'm not going to repeat from scratch the solution. I'm going to use our previous solution in my approach. So that's what nice about EMT. You can always use your experience solving other problem in your new problem solving, new solution that you need to solve. So meaning what? So we have done this problem before. So we know that for surface charge, okay, by using Coulomb method, we able to find the electric field. So but this electric field due to the finite surface charge. Okay, therefore I'm going to use that as my starting point now. So I'm saying from previous solution, okay, so we are going to make it a bit nicer. From previous solutions, for surface charge, this that we did, so the E is equal to the Z rho S H over 2 epsilon naught, and then 1 over H minus 1 over the square root of A square plus H square. Okay, that should be our starting point now. So now how we adapt this solution to our concern here. So what we are really want to solve now, special case where our surface charge is infinite. Okay, so for infinite, so infinite will cause the A to be infinite. That's what it meant by that. So our A now is becoming infinite in order to support the argument that we are dealing with infinite disk. So if A infinite, so I'm going to put A here, which is infinite now, you can see the term here become very, very large. So once it becomes very large, this term will becoming 0. So what we can say, we can see from this solution that the E now becoming what? The E now is becoming Z rho S over 2 epsilon naught. So that should be our standard solution when we are dealing with infinite surface disk or infinite surface charge problem. Okay, so why is Z here? Because our surface before is located on the XY plane. So the Z here meant that the direction of our field always normal to the charge distribution. So in this case, Z. So to make it more general, okay, so in more general cases, the E now can be simplified to be what? The E now will be equal to, the magnitude remain the same, 2 epsilon naught, but the direction going to be the normal unit vector to the surface. So this is going to be our standard infinite surface charge field. Yeah? So therefore, that should be one that we need to remember, and if you can memorize, is good. Yeah? So therefore, that's what we conclude based on surface charge electric field intensity. Okay, let's try one more problem before we end our session here. So I'm going to do problem number 2 now. Okay, so problem number 2 is our concern now. So what we can see in this problem number 2, there are 2 sources. One is surface charge with density 2 nanocoulomb per meter squared. Okay, another one is line charge. Rho L 20 nanocoulomb per is located. So let's write that in more detail. So we have 2 sources now. Okay, question number 2. Okay, so the first source, surface charge. So I'm going to write blue color, rho S equal to 2 nanocoulomb per meter squared, and the parameter is x equal to 3. That should be our surface charge. The second component of the source is line charge. Okay, so let's write in black color now. So now rho L is equal to 20 nanocoulomb per meter, and then the variable here is x equal to 1. Okay, the second component given z equal to 4. Okay, so let's draw our source now. Okay, so let's draw our source. So you can try it first now. You can draw your source first before I show mine. Okay, so draw yours. Okay, I'm going to draw using the standard axis that I have, which is Cartesian axis. I'm going to, okay, this is my z-axis, my x-axis, my y-axis. Okay, so I'm going to call this to be x, y, and z. So blue color representing my surface charge. So x equal to 3, I'm going to draw it. So, but quite interesting here is it does not mention the actual size of our surface charge or line charge. So what we need to do here, we need to make our problem as simple as possible by assuming. Okay, assuming what now to make it simple? Yes, I'm going to assume my surface charge is infinitely large, as well as my line charge also is infinitely large, because we know by assume the source to be infinite, we're going to have standard solution that we have proved before. Okay, so let's do that. So that's going to be my approach now. I'm going to assume it's infinite. So I'm going to call it to be 3 now, so 3 positive I'm going to draw. So this is the 3 where it's going to cross the x-axis. So that should be my intersection. Then I'm going to draw blue color now. So it's going to be something like this. There's no edge. Why? Because my surface charge is infinite. So therefore, the edge is purposely not straight. Okay, what this particular surface charge having? Rho s equal to 2 nanocoulomb per meter square. Okay, that's done. Again, I'm going to draw my line charge. So my line charge now is one line. So what I can see, the x always fixed, the z also always fixed. So therefore, 1 is always fixed. Okay, that should be my 1. 4 always fixed. That should be my 4. Therefore, I'm going to draw the intersection where these 2 points join together. So that should be my point of interest. So the only variable not given by this line definition is y. So therefore, y is variable. So meaning that my line should be parallel to the y-axis. So that should be my line charge. And infinite, I'm going to draw dotted here to indicate the line is infinite. So the question asks us to do what here? Said find the electric field intensity at the origin. So meaning that I want to find what is the electric field at the origin. So this should be here. What should be electric field then? I know, okay, number 1 now. Electric field at the origin, okay, the E now, I'm going to call E total, okay, should be equal to, I'm going to see there's 2 sources, and all the source going to generate its own electric field. Therefore, we have a surface charge, and this surface charge does emit electric field, and then we're going to call blue color now E due to the surface charge. It's one field I can see in my diagram that passing through the origin. Another field I'm going to see that can pass through the origin is due to the line charge. So therefore, I need to sum all this together, and then this should be my final solution. I'm going to say to myself, the E at the origin, actually the E due to the surface charge plus the E due to the line charge. And both charges are infinite. And we can see now, so I'm going to draw now my E rho s now. Remember, when we have infinite surface charge, the E must always normal to the surface. So therefore, normal mean what here? Mean this direction. That should be my E rho s. Okay, that's what we have proved before. It's normal to the surface, 90 degrees. So what we can say straightforward, E equal to rho s divided with 2 epsilon naught. And what should be the direction of our E from the diagram? Good, negative x, done already. So what should be our rho s? 2 nanocoulomb. So just substitute that value to our rho s. So that's done. Okay, let's do for the line charge now. Remember, when you have infinite line charge, what does it do? The E also must be perpendicular to the line and passing through the origin. So what I can see from my diagram, my E is going to be in such pattern. So this should be our E rho L. Why? 90 degrees to the line charge. Okay, so let's do the mathematics now. We're going to plus E, which is rho L. Remember the formula for infinite line charge? 2 pi epsilon naught. And what should be the direction now? So this should be 1. So the magnitude now going to be this component square plus this component should be what now? 16 plus 1 should be square root of 17. Okay? Because 4 power of 2 is 16, plus 1 power of 2 is 1. 16 plus 1 should be 17. The square root will going to give us this magnitude. Because remember, the R is the distance between this point to the location where you want to determine the E. And how about the directions? Okay, the direction, you have to be careful now. The direction should be, okay, it's moving downward, so it's going to move this direction. How many? So what should be? So it should be negative x, because 1 is the magnitude. Then moving downward, what's the magnitude? Should be negative 4z. And remember, we are substituting unit vector or vector? Yes, unit vector. And always remember, you need to divide everything with the magnitude, which is 17. So with that, that should be the solution of our problem number 2. Okay, so there you are. So I just shown you the approach, how we deal with finding electric field due to surface charge. Okay, the last source that we dealt with in electrostatic is the volume charge. And volume charge, so if you refer to the handout number 4 as well, there's one problem that referred to volume charge. Okay, so this is the problem that I purposely placed in my handout number 4. But I'm not going to solve this problem here, because the mathematics is going to be quite interesting. And another reason why, because I can still solve the same problem using much simpler laws or theorem. And that theorem we're going to learn later on after this. So that method going to be much more preferred method we are dealing with volume charge problem. Because why? Much simpler mathematically. So that going to be discussed in next lecture. So hope that you're going to take this opportunity to familiarize yourself with Coulomb's law, because Coulomb's law going to be one of the questions going to be asked in your test 1. That going to be, I think, planned in the week number 5 or week number 6. So we're going to inform you regarding tests. So please prepare yourself, because that's going to be one of the questions in our test. By the way, we're going to have quiz this week. I'm going to give you the question, then you need to answer them and then submit your solution to me. So the detail about how we're going to handle the quiz going to be posted in my e-learning. So thank you very much. So take care and be safe. Assalamualaikum warahmatullahi wabarakatuh.